Okay, so good afternoon to everybody and welcome to the event Horizons of Quantum Computing. So unfortunately, the president of the class of Physical Sciences of the Academy, Professor Contucci, will not be here today because he's not in Bologna, but he's sending his greetings. So in the past few years, probably many of you heard a lot of talking about quantum technologies and a lot of possibilities, but sometimes if you look at general news, it's hard to understand what really can be done and what is just hype. So the idea of this event is to that you have a closer looking at what can and what cannot be done and try to understand a bit more what are the realistic perspectives of the field. So we have a list of 4 speakers and we can begin with Professor Marco Barbieri. So he is currently full professor of physics at the University of Rome 3 and is leading the research activities in quantum optics and quantum information. So he got his PhD at La Sapienza in Rome, and he worked mainly on experimental quantum optics, and in particular on the use of single photons for quantum communication and imaging, and in general on photonic technologies. And he made significant contributions to the development of practical implementation for quantum information protocols. So he will talk about sending out an S+OS on communicating quantum messages. Okay, so please, Marco.
Can you hear me? I think so. Good afternoon, everyone. Let me start by thanking the organizers for inviting me in this fantastic venue. I'm impressed in being in such a historical place. I have to come clear, I won't be talking about quantum computing proper, but in a broader sense about quantum technologies. And I dare not venture into a field which is not exactly mine, like quantum computing proper. And I decided to stick to what I actually know, which is communication. And I think that the best way to convince you about the relevance of this topic is to ask you, please, to take your phone out. Take your phone out, please. Just visualize all the information that it contains about you. The messages, the funny pictures, the jokes that you've made, all that tells about you and your life. And think what it might happen if that fell in the hands of your mom or spouse. If you're living La Vida Loca, you stick to this phone, not the other phone that you use. See, that slight feeling of unease and embarrassment, that is the best explanation I can give you for why it is important to hold your data secure from hands that you don't want them to fall into. And in order to achieve this, we shouldn't be shouting out loud our secrets, but rather we should use keys to encrypt messages. If something is sensitive, if something is important for us, and not everyone should be able to know that, then we have to use a secret key, which is the founding technology that we use when we are sending out, say, we are doing a purchase on Amazon, it has our data recorded. When you exchange information with their server, it doesn't send our data in plain text, it codes them. It uses something which is called a key. So the problem is now to protect the key. You don't want to send the most sophisticated encrypted message and then the plain key. Everyone would be able to break that. And throughout history, there have been essentially 2 different approaches to how to distribute the key. The first one is relying on the physical security of the device. You know what that is? Indeed, it is a skytail or a scutale, as the Greek would have called it. It is a device that the Spartans in particular used to encrypt messages. So they would take this parchment and wrap it around a stick of known dimension, and they would then write the message on the parchment, unwrap that, and send the parchment without the stick. Then only if somebody held an identical device, they would be able to read the plain message. It's not the best way in which you can encrypt a message, but yeah, very good, very good. But there are two difficulties in that. The first one is that the secrecy resides in how the device works. And the second one is that if you want to ensure that your encryption works, then your device should not fall into the hands of somebody you don't want them to read your message. So you are trying to hide your message from somebody. This is what you are doing, which is not the most secure way in which you can approach the problem. You should follow instead Poe's recommendation in his very famous novel, the Perlin letter. You shouldn't hide things; they should be in plain sight. This approach goes against that, and it is not that far-fetched. Part of the reasons why the French and English could break the Enigma code is because they could get hold not of the devices but the plans of the devices from Polish refugees early on in the war. Without that, Bletchley Park would have been completely useless. Instead, we can focus on something else, which is the algorithmic security. We do not rely on the physical device, but rather on mathematics. So secrecy does not rely on something working in an obscure way, but rather in the functioning of an algorithm. Once again, this is not new. That you know what that is? It's called Alberti's disk from Leon Battista Alberti, among the other things, very famous architect of the Renaissance. And that is used to encrypt text by means of Caesar's code. You have the external ring, which has letters, the internal ring that has letters and symbols, and you could shift the encryption. And by turning the disk, you can change encryption for every letter, for instance. But even with all the sophistication of that, that is a very fragile thing. It has been discovered that that kind of encryption does not work. It might seem, if you're in kindergarten, that's brilliant to encrypt your messages, but yeah, if you're trying to win a Renaissance war, not much. Now, where does the asymmetry in information between us and our adversary resides? In the fact that we have extra information that we hold private, and without that, cracking our code is hard. In this example, you would change the alphabet each and every time, and figuring out how you change that would be hard for your adversary. Turns out it is not, but that's the detail. It's a shift with respect to what we had before. We don't rely on the mechanism of the device itself. We can replicate that with pen and paper, or pencil and paper back then, and still it works. But hardness is a relative concept. Well, you're probably too young to remember the Millennium Bug. I don't know whether you heard about that. Back in 1999, yes, there have been years that did not start with a 2. There was much fuss about the possibility that computer systems would crash because back in the 80s, we only used 6 digits to write the dates. So there was the risk that at the midnight of December 31st, 1999, all the clocks would be set back to 1900s. And that would have caused massive disruption. It did not happen. In the end, we are here and our machines are working safely. But back then, in 1980s, saving 2 digits was a big deal. It was a game changer in terms of optimal usage of memories. Nowadays, things have changed. And this implies that if I figure out something which is good enough these days as something which is hard enough not to be cracked by present material, it might be so in a few years. And if I want to get hold of very sensitive material, I can think of downloading my messages, my encrypted messages now, and in 10 years, I might be able to crack them. So we want to avoid that. So you don't want to rely on a specific device. You don't want to rely on the fact that you are hiding that from the rest of the world. And you don't want to rely on the algorithm entirely. What can you do? Well, you can completely change the way you approach the problem and try to ask fundamental physics to save the day for you. You are not relying on the functioning of this specific device. You're relying on the functioning of nature. You are trying to ask your adversary not to do something which is hard in order to break your code, but actually something which is forbidden by the laws of nature as we know them. And if you're smart enough, even by laws of nature that we should yet know. This is where quantum physics comes in. And it comes in through this door, through the secrecy being rooted in fundamental physics. And that's because this is the most fundamental theory we have to look at the natural world. We are trying to use that in our favor in order to crack codes. Where is the gotcha? It is in the uncertainty principle. I guess some of you are being scientific minded or at least scientific curious. You must have heard about that. And that's the standard formulation that you must have seen a million, a gazillion times perhaps. And this is the effect we rely on to prevent our adversary to crack our code. And that is a very fundamental cornerstone of quantum mechanics. Some may say that it is a very trivial consequence of the formalism. Either way, you can't not escape that. That is there, it's rooted in the theory and from what we know in the fundamental physics. So that is real, you cannot go beyond that. What does it say? Well, not that. It says that, say you have a quantum object and you have 2 properties of it. It can be the position and the speed. This is the standard example. Alice is the one who's sending the message. She wants to send the key. She wants to establish a key with another partner. And so she decides, okay, I'll take my object and prepare it in a very specific value of the variable x. Say it puts her system exactly here, in this position, very precisely determined. She is forced not to determine its velocity, but its speed, sorry. What it might happen is that this quantum object will have many possibilities for its speed. The more you localize, the more the speed should be indeterminate. And the difference with the classical world is that all these possibilities for the velocity having this value, this value, this value are present at the same time in the object. It's what we call a quantum superposition. And if you're localizing x, the state is not localizing p. If you have decided where to put the state, you cannot say what its speed will be. And the other way around. Alice can decide from one round to the other to change not only the symbol which is written here and which will be part of the key, but the way the symbol is written. So she decided she prepared something which is going at exactly that speed. But that means that in space, it should be delocalized. It can be here or here or here or here, or better, it should be in a quantum superposition of all these possibilities at once. But if the receiver decides to measure in this case, the velocity rather than the position, they will nevertheless see one value. They won't be accessing the whole superposition. They are bound to take one value, and the superposition will collapse, as we say in our awful jargon. So what happens is that Alice decides to write a symbol, or in either X or P, she sends through a transmission channel the symbol to her partner Bob, that decides whether to read the X property or the P property. Regardless whether there be a superposition or not, Bob will always receive one symbol to the transmission. It might be exactly the symbol that Alice has sent. It might be a random symbol. Nevertheless, he will see one value. And in those cases in which Alice and Bob, just by chance, happen to have chosen the same physical property for writing the symbol and reading the symbol, then they'll agree on what that is. If Alice decides that symbol is 0, then Bob will receive a 0. If Alice has decided that that symbol is 1, Bob will see a 1. But that has to come as a lucky chance. So Alice should not give out means to predict what should be doing, nor should Bob. So whenever that happens, everyone is fine, and that symbol will be part of the key. Everyone's happy. If not, if Alice decides to say write on P, and Bob decides to write on X, then that round is thrown away. Let me remark that Alice and Bob only need to say to each other what choice of X or P they have performed. They never need to communicate what is the actual symbol that they have used. If Bob has seen a 0, he doesn't have to tell Alice, okay, yes, I've seen a 0. He has to tell that he has chosen the X basis, the X option, for instance. So these symbols are never revealed. It seems that not only the key can be established, it can be established in a private way. As I was saying, if Alice has decided to write on P and Bob measure on X, he will receive a random message. Alice cannot figure out what exactly is the symbol that Bob has received, so that round has to be discarded. It works brilliantly, but not all the times. Then we now allow for an eavesdropper, someone who is interested in spying on their conversation, getting their key to be in between, to intercept the signal and resend the signal. And we do not put restrictions on what technology she has. Nevertheless, there are restrictions that come from the uncertainty principle. She can do whatever she wants. If the eavesdropper can do whatever she wants, but she'll never break the uncertainty principle. And so, if she intercepts a message, saying measuring in the wrong observable, Alice has written on this variable P on speed, but Eve decides to read the position instead, she'll get a random number. She doesn't know because Alice has not announced what her choice was at first. And the best thing that Eve can do is to write something on X. But if she writes something on X, that means that P is completely undetermined. And when Bob finally receives the message, then he reads essentially a random number. What might happen is that if Alice and Bob decide to sacrifice part of their key, they can check whether there have been errors in the transmission. So sometimes Alice not only says that she has used speed, that she reveals what speed she has used. Bob used that to compare, and sometimes there'll be errors. If these errors are present, then something funny has been going on, and they infer the presence of B. And this is because it can only choose one variable to be read. She cannot assess X and P at the same time. The uncertainty principle does not allow you to do that. So she is forced to introduce those errors, and through those errors, Alice and Bob can infer her presence. This is how quantum cryptography works. Let's be clear. We are relying on the fact that no matter what the eavesdropper decides to do, no matter how technologically advanced she is, she'll always have limitations. And these are natural to the fact that nature, what we know, obeys quantum mechanics. The countermeasures that Alice and Bob adopt are not much about pretending that Eve is not there, that eavesdropping is not occurring, but rather to detect its intrusion and give an idea of how intrusive that is. But we've seen that not all rounds are acceptable. Not all rounds are devoted to establishing the key. Some of them just need to be thrown away because Alice and Bob have not agreed, cannot agree, actually, on what choice, on what choice of observable they should have. Absolutely. And then they have to figure out what, if there have been errors. So they have to establish the key afterwards. So this thing is computationally very intensive. That means that you cannot achieve high key rates with that. They're effective, but they're very small. Then, now, we need something to transport that information. And light is an excellent carrier for this sort of quantum information. We can use photons that are elementary particles, the electromagnetic field, so to speak. And being particles of the electromagnetic field, they inherit all the physical properties of such fields. There are red photons, as we have red light. We have blue photons, as we have blue light. We have polarized photons, as we have polarized light, and so on. Plus all the quantum properties, which means, in brief, that they have to obey the uncertainty principle, by and large. Now, what are the actual choice that we use? In the coding, we do not use position. Well, we could use the position and the direction of propagation with photons, but this is very uncomfortable to be transmitted in through fibers. You should localize the photon within your fiber, and that kind of signal is very disturbed through propagation, so hardly anyone does that. Sometimes you rather use the polarization of those photons, which is the direction of their electric field. So you can use the direction of the electric field, whether it oscillates like this or like this. It's one property, and the rotation of the electric field, whether it rotates clockwise or counterclockwise, is another property of the field. Those two are related to its sort of uncertainty principle relation. It's not exactly like that, but it's close enough that you can rely on that. Or you can use energy properties, which in the language of photons is their color, and time properties, and also all these are linked by an uncertainty relation. But let me remark that we are relying on the fact that these properties are actually the quantum superposition of those properties and vice versa. So the quantum link is through this fact. A photon that arrives at a specific time is in a superposition of many energies. A photon which has a specific energy can arrive at multiple times. Or I should say its wave function contains all the arrival times at once. And generally, this is the doublet, the couplet which is used because it's very robust. when you adopt transmission through fibers. Sometimes people use this when transmitting in free space links, for instance, from satellites. That is good enough. How do we produce single photons? Well, we can do that, but this is very advanced technology. If you want a real single photon source, then you have to rely on very sophisticated engineering of semiconductors, way more advanced than we use, for instance, for this machinery. And more crucially, they have to operate at very low temperatures, something which in the best case is 4 Kelvin. And it's not only columns, it's huge cryostats like this one, which is depicted. To give you an idea, the distance between those two walls is 5 centimeters. So this is chunky and also very expensive because you have to bring that to the temperature of liquid helium, and we ran out of helium. So it has become a strategic material, which costs something like 15 euros per liter, something like that. Way more than, but almost as much as fuel these days. So you can understand this is not the optimal solution if you want to make a distributed network. Can't we use something more common like lasers? No, not strictly, because they contain more than one photons. And that means that there are multiple photons present in the emission, and that they will ultimately give out more information to Eve than to Bob. But it has been discovered, well, it has been mentioned, that has allowed to some extent to replace these real single photon sources with ordinary lasers. And the idea is very simple. Well, I know that Eve is out there lurking in the dark. Well, why don't I use some of the rounds as decoys? I'm not using them to exchange information, just to reveal her presence. And remarkably, simple as it is, it works. It works really fine. This is the thing that has changed the reach of quantum cryptography networks. You can do that, and there is a significant advantage. So say this is the transmission distance which you can go, and this is the key rate generation, which means that if I am 20 kilometers away from the source, then I can expect to extract, let's start 10 to the minus 5 when, well, not much, but 10 to the minus 5 symbols for every round, which means that I have to repeat that for a few hundred thousand times if I want a sizable key. But if I now reach, say, 30, I cannot get any key. If I use decoys instead, well, I can reach much further. I can reach up to 140 kilometers. It's not the most spectacular key, perhaps. Maybe I want to stop at 100 kilometers, but I can get there. And I think the lesson to be learned here is that if you have a problem with your device, you don't necessarily tackle that problem by improving your device. You can improve your theory. You can cope with imperfection. That might be a more effective way of establishing a secure link. Where are we now? In Europe, there is a project called, an umbrella project coordinating some local projects. So the way that EU is supporting this action is by coordinating local actions that might involve a few countries. So we are building a network of networks. The EU thought that this would be the most efficient way. If you have this bottom-up approach, trying to build your own network and then merging them together, rather than a top-down approach, for which probably the Commission would have no means. And this action, the EuroQCI, has been going on for quite a while and is starting to bring out a very interesting results. Not all countries have approached that. Chinese, of course, are much more, have taken the other approach, some top-down approach instead. in the early 2000s, some optoelectronic departments were turned into quantum science departments because the party decided so. But they've also been very effective in launching a satellite. It's called Misius, from the name of a very illustrious Chinese philosopher, which I knew nothing before the launch of the satellite, that has in it a proper quantum light source. It's not the kind of quantum light source that I've shown, but nevertheless, there is real quantum light coming out of the satellite, and through that, they could make a connection from Austria to China using their telescope stations. This distance is some 8,000 kilometers, more or less. Very impressive result. How can you go further without relying on satellites? Well, now direct links can reach, say, 200 kilometers. That's probably a very optimistic estimate. And what can we do beyond that? Well, what we do with classical communication is that we amplify the signal, we repeat the signal. We cannot do that with quantum light for two reasons. First, it is forbidden by quantum mechanics to do that perfectly, but even if you do that imperfectly, you end up adding noise, which you don't want, and you give out more information to your eavesdropper, which you don't want. Nevertheless, there is the possibility of building quantum repeaters. It's just that they'll be very different from what we intend as a classical repeater. Probably we'll hear more of that from Francesco. But take a message from this slide is that we will need something that's like that in order to extend that reach. And as we hear later on, that relies on coupling our photons, our light, to matter in some way. So what we can foresee in the future is that Alice won't be talking directly with Bob. She won't be exchanging the key directly to Bob, if not on very short scales. But I mean, with 200 kilometers, you could perhaps reach Florence, certainly. Perhaps Ancona, certainly not Rome. So it's a short haul, but they'll pass through a series of connecting nodes. And it's very likely that in the first implementation, those nodes must be secured in some way. Maybe you want to put a guy surveying this or something like that, using my strike in order to be sure that there's no one tampering those things. But that means that we'll have to trust those nodes. Well, there's a subtle point. Let me go back to the scheme that I've shown you before. And the idea is that, okay, Alice decides that she writes a single on B, he reads X, and she's not bound to be sending out a single photon or an activated photon or an activated beam. She can send an intense laser. And there's a point of discontinuity here because Bob needs to do something. He has to rely on something which is able to capture those single photons. And if you use a very intense laser on single photon equipment, you can start doing funny things. So even if in principle, it could not make any successful attack or partially successful attacks, if she stays if she doesn't break Bob's devices, well, she might just scan, she might just try and well, maybe not break, but certainly modify the behavior of Bob's equipment, which is not meant to be taking this much energy, this much light. And that has been realized in the early 2000s, that there were these side channels, so they're called. So something which is not, some things that are not directly linked to your protocol, but they're there anyway. Like we use the fact that Bob has to use single photon detectors, and Alice can, and then Eve can just send, get zillion photons instead. And if we start thinking that we are chaining nodes after node, well, that opens the possibility of opening more side channels. Well, once again, the solution does not come simply by trying to improve on things, but rather to embrace those imperfections and including them in the theory. And there is the possibility of gaining some security to some level if instead of using detectors, which we've seen are not secure, well, not intrinsically, you ask Alice and Bob to write a symbol, and then you have a node which does not need to be trusted remarkably, and do some checks for that. In this way, if this untrusted node here checks whether what Alice and Bob have sent is doing interfering in the most classical way, like this, well, you can still rely on such a scheme to establish a key. I won't get into the detail, just focus on the idea. And in this way, the security might not depend to a large extent on the specifics of this untrusted node. You need to know what this does. And still, if you're using proper quantum equipment, then you can still establish a key. Yep. And this is called a measurement device independence. This has been tested in the experiment. I know that connecting a Bardonecchia to Santiago doesn't sound like for the far future, but it is. This group at Ingram with support Toshiba, they could use this idea of having an untrusted node in between in order to extend the reach to 200 kilometers. And the Chinese have done so by linking Jinan and Qingdao with a link that is 430 kilometers long. If you wonder what those two cities are, just look at the insert. Why is this linked to computing to some extent? Because you can envisage this scenario in which Alice has limited power. She can only send some quantum data, but the biggest chunk of the computing will be performed by Bob in his cloud computer. She'll send the process data back, and more often than not, Alice would not want Bob to figure out what she has done, and Bob must have no way of storing that information into the server. And there is the possibility of doing that. This is a recent experiment that has been performed at Harvard University, in which Bob has a computer which is done with diamonds. It is programmed remotely by Alice, and then Alice receives the information always via photons, and Alice can perform the computing using Bob's server without revealing any information to him. This is called blind quantum computing. Or we can rely on similar physics, like in such case, we have Alice. She wants to take the image of something which is sensitive. So she uses quanta to form the image. So we have light going in, light going out. We can think that since the physics of these photons is the same as the physics of the photons that we are using for cryptography, we can rely on the same mechanism in order to ensure that this light comes in unaltered and has not been tampered by someone. And this is a not so recent, but still interesting experiment from the University of Glasgow. These are the images. These are the images, original images. This is what they could retrieve using quantum correlations in the background. And this is what you can retrieve, which is nothing if you don't have access to those quantum correlations. To conclude, what lies ahead? I won't be talking about the technological process that we need. I'd like to finish with some more high-level considerations. First of all, we should be serious about developing statewide, nationwide networks. That means we not only have to deploy the quantum fibers to some extent, or adapt existing fibers to quantum communication. There's more that we can do. We cannot rely on GPS for timing, for instance. And that is a massive investment. We'll see whether it will happen or not. It sounds likely. The other piece of work that we have to undertake is to ensure that we have a standardization procedure. Somebody that certifies that this device is, yes, it is secure to this extent, and this device, well, it's only partially secure. We desperately need that want to build a serious industry. It's not that there are no companies selling quantum cryptography devices, but there's no standardization, nor at the European nor at the US level. Not sure that they have that in China. I'm not sure that they need that in China. And I think that the most subtle point, the most important point is that we should, at this point, we should probably stop thinking about sectors that do not communicate with each other. There is an environment which is that of quantum technologies, and we should think of what we can do by merging things together. If we want a network of quantum sensors, then we need to control the sensors, and we need to control the communication, or with quantum, if we want to interface quantum computers in a cloud, we need them to communicate. And I think that that's the most intriguing challenge ahead for the next few years. With this, I thank you all for your attention.
Questions from the audience? Also online? Okay. So if not, we can thank Marco again. Then we can welcome. Okay. So our second speaker is Professor David Gamarnik from MIT. So he's now full professor of operations research at MIT, and he received his PhD in operations research at MIT, and is widely recognized for his contributions to applied probability, stochastic processes, and the theory of algorithms. And his research is mainly about fundamental questions in optimization, both classical and quantum, random structures, and computational complexity. And he got several prestigious awards, and also he's been a leading voice in assessing the limits of algorithmic performance, both for classical computing and quantum computing. And today he will talk about quantum overpromise for optimization.
Thank you,
David.
Good afternoon. Good to be here. Thank you for Giacomo for the invitation and the fantastic opportunity to interact with the audience in this kind of a less than technical way, and that's the way I want to sort of keep the talk in spirit. So first, as a disclaimer, I'm the least qualified among the four speakers here. I'm the least qualified to talk about quantum technology. This is a relatively new field for me. I've started working on this about maybe 5 years ago, and I'm 57, so it's really I don't know what I'm doing. So for I take my hat off to my colleagues. They know much more experience, much more knowledgeable. My field of expertise is more in the whatever is called optimization. That's what I want to talk about primarily. So I don't know much about quantum science, but as the joke goes, I don't know what it is, but I'm happy to explain it. Just to explain the figures, this is Richard Feynman and this is David Deutsch. These are founding fathers who conceptualized the idea of the quantum computer. And this is versus Alan Turing, was obviously founding father of the classical, as we say, conventional computers. So this is my outsider's perspective on the quantum computing. I think this is one of the greatest scientific and engineering challenge of our time. This is what personally brought me to the field. When I learned about the questions, mathematical, algorithmic, business, or across any way you look at it, as a scientific and engineering challenge, it is amazing. At the same time, I don't think it's a good investment opportunity. So if you're thinking about buying D-Wave machine to churn money, make profit out of it, I would say, think again, right? And I'll try to justify my position on this through the lenses of the field called optimization. So if you already bought it, if you already invested in big, giant quantum computer, I would say, thank you very much, because you're doing a great service to the society by advancing the science and technology and helping folks like my colleagues to do a great scientific discoveries. But please do not expect, despite the hype, I want to de-hype it, don't expect that this technology will churn money soon. And let me justify and explain why I stand on this position. And as the time goes, the more time goes, the more stronger I stand on this position. It's also a limited perspective, so I want to also sort of premise it by that. If you read about popular description of quantum promise, basically, where do you expect the quantum computers to make the greatest dent? Basically, where do you expect them to be the most kind of effective? You would find perhaps the following areas. One often quoted area is the quantum chemistry. I'm not a specialist on that, so I'm not gonna, I'll be careful about sort of commenting heavily about that. However, if you dig down deeply into that, there's something suspicious about the promise of the quantum progress in the quantum chemistry as of now. And I'll explain what it means. The second often quoted, and this is what brought me to this whole debate, area is the so-called optimization. And that's the area of my expertise. So I'm kind of qualified to say something about that. But there are other areas. Cryptography. That's the previous talk. That's, fair game. So I'm not going to, obviously comment on that. We already heard a great talk just before. Finance and investment has been often quoted as, for certain reasons that we will discuss, as one of the most promising area of application of the quantum computing and quantum technology. And I'll say why, but not now. And last but not the least, but this is not the full list, but last in my list is artificial intelligence. It is quoted and it's stated many times that quantum technology is extremely promising, specifically in the areas of machine learning and artificial intelligence. And if you dig deep into that, and we will to some extent, we will see to what extent we should actually expect that to be the case. All right? Okay, so I guess I'm kind of a Mr. Negative here. And as Giacomo already said, I also work on classical negative results. So now I'll move to the quantum negative results. So maybe some people hate me for that. I'll take it. Let me do a gentle introduction to the field optimization. Optimization, well, optimizing something that is very natural to us. We want something better, best, and so on. But it's actually a scientific field. So let's do a quick walk over that. What is optimization? We use optimization in our daily lives all the time. So if you use the GPS and find the shortest route between A and B, that's optimization. Well, it's done it's done for you on behalf of you by the technology, but it's somebody somebody solving this problem for you. How to go from A to B in the shortest time. You go on a trip. You try to pack the largest number of useful items in your bag. There's a limited capacity, but you want to make the most usage of it, most utility of it. That's an optimization problem. Internally, you don't think of it maybe this way, but in fact, it is a special, an example of optimization problem. Or you try to sort of manage your money in best possible way, so you optimize your portfolio return. This is admittedly a little American-centric here as an example, but probably here as well. It doesn't mean that you solve this problem, but maybe professionals, financial advisors solve those problems for you. But optimization is also a huge multi-billion-dollar industry because it's used across the board. Historically, the earliest use of optimization is in military. I'll talk about that. In airline scheduling, transportation, Uber and Lyft rely on very sophisticated version algorithms for optimization all the time. Facility location, online advertising. When Google decides which Google, Facebook, any online social media, when decide which ads to put, there's a deep, complicated algorithms to figure out what is the combination of online ads that will make the most money for the company, right? Workforce management, financial investment, as I mentioned already, and many other examples. Okay, it is a scientific field. It's a mathematical field, and it's actually pretty old. I'm not a historian, but sort of roughly speaking, one could say that the earliest scientific approach to optimization goes back to Newton, because he invented calculus, right? And maybe you remember, I know I'm not supposed to expect you that you have scientific degrees, but maybe, calculus and derivatives, how do you find the largest point on a curve? You set the function, derivative, and you see which point gives you the largest value among the points that have derivative equal to 0. And this is how you do that in high school or college when you take calculus. But in fact, in modern usage of optimization, perhaps there's a new phase or era of optimization that started after the World War II, when George Dantzig invented something called linear programming. Linear programming is called programming, but it's not the programming in the sense of coding. It's a programming in the sense of the algorithms. He was solving a big transportation logistics problem for Navy. He was trying to figure out how to best ship the whole bunch of different items to the Navy locations. This was 1946. And he figured out a very clever algorithm to do that called linear programming. And that's the beginning of the modern scale. Why is that application important? Because it's the first time that optimization was thought in terms of a large scale kind of big data type of environment. Here you're really optimizing over one variable. It's kind of it's like smallish enough that you can do kind of by hand. Starting from this area, optimizations are solved with a huge number of different variables and possibilities. As it turns out, I promise this is going to be the only math in this talk. Optimization, it's a principal scientific field because you can reduce it to some extent, you can reduce it to the case of linear or so-called non-linear optimization problem, which looks something like this. You try to maximize some quantity, like the value of your portfolio, but you have some constraint, like you don't have more money than you have. And then you write down those constraints and so on, and then you give it to the computer, and then hopefully you have a good algorithm, and the computer toggles those numbers, makes sure that constraints are satisfied, but tries to make this as much as possible. So that's an example of optimization problem. But let me give you an even more concrete example. Here's an optimization problem which does not involve any equations. It's really a game, very simple one. You can play with your kids, right? I tried it with my daughter. She didn't like it, but maybe you have a better luck. So you have circles. It's very simple. You have circles and you have connections. These are think of them as members of the social network, and connection means that they're friends. Okay, and your goal is to find the largest number of non-friends. Right? You want to find the largest number of non-friends. Why? Turns out that this has many applications in various across the board. Let's leave it aside. This is a really interesting practical optimization problem. Right? Find the largest number of circles. I'm not going to torture you how to do that. I'll just give you the answer. In this case, you can just manually sort of play and find out the combination. So it turns out that you can find 10 out of 16, and notice that I did not violate any constraints. So no two blue dots are connected by a match. All the blue dots are non-friends. By the way, if you have any questions, I'm happy to pause and answer questions during the talk. No need to wait till the end. Okay, let me give you one more example. This is an example that I use with as students when I teach optimization at admittedly very elementary level. This is a really portfolio optimization question. So suppose you are considering investing into a combination of 20 projects, and you have investment amount, and you have a budget $220 million, let's say. You can invest up to $220 million. This is the invested amount for each of the projects. So this project would cost you $13 million, $30 million. And so of course, you have to stay within the budget. And you want to maximize the profit, and the predicted profit figures are reported in Q3. Okay, and the question is, what's the best combination? Believe it or not, you can solve it on Excel in a split of a second with optimization technique, non-quantum, very elementary. You can solve it in split of a second, formulate and solve it on Excel. Excel has optimization method, optimization algorithms, and that's the best result. Turns out that you need to invest in project 2, 3, 6, 7, and so on and so forth. This problem involves 20 so-called decision variables, numbers to toggle. But modern optimization applications involves thousands, tens of thousands, and millions of variables. And Gurobi, one of the leading softwares that, the leading software in this area is Gurobi, can handle millions of variables. And that's the scale that companies really need to solve those problems in applications. So these are 3 examples. There's more examples. I could give you more. The list goes on and on and on in airline scheduling, in project matching, and finance, and so on and so forth. So where's the quantum promise? Why is that? Why do we could believe that quantum computers could give us the edge over conventional computers in solving these kind of problems, large-scale problems involving thousands or millions of decision variables, right? This is not. Let's try to understand it, right? It's not a very dumb idea. It's actually pretty clever. There are clever reasons why one would expect something like this. At the very least, let's think about the skills of conventional computers in terms of, for example, the memory capacity versus quantum computers. I'm going to do that without introducing the formalism of quantum computing. I will just tell you the implication of what the quantum technology can do, for example, in terms of the number of states that it can encode. So the conventional computers, if you have n bits, you can encode 2 to the n different states. And this is how sort of your memory scales. This is why we quote memory of your computers in terms of, gigabytes, terabytes, and so on. The terabyte is that many bits, and modern PCs have about 2 to 1 to 3 terabytes of memory. Now, the fascinating thing about quantum computers and quantum technology is that the number of states that it can encode, roughly speaking, I'm not very precise here, my colleagues might correct me, but roughly speaking, it grows doubly exponentially in the number of qubits, which is the quantum analog of a bit. Right? The number of configuration, because the quantum computer, as you may have read, if you read something about that, it works in a superposition of states. It works in the superposition of the classical so-called bit configurations. I have a picture to illustrate that. But just to appreciate this sort of the growth, I've put some numbers here. So how much you can get with qubits versus bits. So with 5 qubits, with that kind of growth, you can get that many states. So with 10 qubits, this is equivalent to the 1,000 conventional qubits, because 2 to the 10 is about 1,000. So that's the growth. And if you have 40 qubits computer, that can encode anything you want, potentially. With a scale like that, it makes very reasonable that if the computer can juggle such massive things at the same time, it should have an edge. So that's the idea. It's a very reasonable idea, no? The way quantum, but the scale by itself is not the answer, right? The way quantum computer works, and this is just one quick slide, and I'm not expecting you sort of to parse through this in a detail, but the way quantum computer works is that it creates a superposition of classical bit string configurations and starts kind of rotating them in some way. You engineer, your algorithm is supposed to engineer to rotate them in such a way, such that in the end you obtain configuration which after so-called measurement produces a good solution. What is a good solution? Optimal portfolio, optimal dots, non-friend configuration, whatever is your optimization problem or whatever is the problem that you're trying to solve. Because the quantum computer can operate, it's kind of like operating on all solutions at the same time. You just have to rotate it cleverly enough so that it finally arrives at the solution that you want. But then you have to engineer it so that it arrives at the right solution. Can you do it theoretically? Can you do it practically? That's what I want to talk next. Right? There is a reason for optimism. First one, let me lay out why it would be reasonable to expect the supremacy, as is often quoted, of the quantum technology. Supremacy means advantage. It's a term coined by John Pascal, very nice, clever term that captures the idea that the quantum computers should be supreme, more effective than conventional computers. What is the reason for supremacy? One thing is memory. We already talked about that. There's many success stories. Perhaps the most famous one is the celebrated Shor's algorithm that gives a quantum algorithm for factoring numbers, and it's a staple of cryptography that to the day, no classical, no conventional algorithms can match it in terms of theoretical performance. Shor's algorithm is not yet practical because to make it practical, you need way many qubits that we have currently. But theoretically, it's a startling achievement. There's no doubt about that. It's not the only success stories. There are other success stories, like maybe lesser known, but so-called Grover search. I'll skip it what it is. And there are other stories in terms of the sampling quantum states, supremacy, and so on. Offline, I'm happy to talk about that. On the practical side, there is also big progress has been made in terms of building stronger and more larger quantum computers. And nowadays, the figure I see quoted is about 500 to 1,000 qubits. Of course, we understand the number of qubits does not directly translate into the performance and optimization, but the more the better. No doubt about that. Many companies spring that invest almost exclusively in building quantum technologies. Some listed in here, some maybe usual suspects. Many companies build research groups, like many finance companies build research groups. Amazon has a quantum research group. JP Morgan has quantum research group. Major investment banks in the US, maybe not only in the US, build quantum groups. Why do they do that? I suspect they anticipate some kind of fairly quick advantage edge in solving the problems that they care about. We'll see if this is something that's actually justified. And what perhaps bothers me even more, quantum supremacy is often quoted as a present-day reality. Almost on a daily basis, I see Google Scholar recommends me based on sort of what I care, sort of my reading and what I work on, recommends papers that claim construction of the quantum algorithm that is stronger theoretically or practically than conventional classical algorithm. And that that was kind of that was now a bit of a red flag for me. So I decided, okay, I need to understand what is going on. To what extent these claims are actually valid and justified. What are the issues with quantum technology? If you read about the challenges, one of the most quoted one is the issues of the robustness and the coherence, engineering challenges in making the computers fault tolerant, error free, and so on. And a lot has been said about that. I'm not going to comment on that. That's a definitely big challenge, engineering challenge that needs to be addressed. And I hope that sometimes this will be addressed. But that's not the issue that I want to discuss today. The issue one of the issues that I want to discuss today is benchmark. When you say that your quantum algorithm or my quantum algorithm, somebody's quantum algorithm is better than conventional quantum algorithm, how do we do this comparison? What do we compare? Right? This seems like should be an obvious. It's not a very obvious question. Benchmarking is actually a pretty tricky thing, and even within the classical conventional computers, properly measuring performance of one algorithm versus another algorithm is science by itself. It's not a very straightforward thing. Number two, as it turns out, there's also theoretical barriers for quantum algorithms in the field of optimization, at least within the so-called NISQ type, noisy intermediate type quantum devices, quantum systems, within which is a class of quantum algorithms for optimization, which is supposed to be built pretty soon because it involves less, it doesn't require that much fault tolerance and so on. We'll talk about that. Turns out that there's a theoretical barriers to that, and that's my line of work. Barriers which apply to both quantum and classical algorithms, in pretty much mathematically meaning that quantum computers cannot overcome those barriers, but below those barriers, even classical algorithms approach those limits. So that leaves almost no space for the quantum improvement. I'll give you an example shortly about that soon. False alarms, I already talked about that. The evidence for the quantum supremacy, for the optimization, I want to stress, I'm talking about optimization areas, is quite shaky because of the benchmarking issues. You start digging deeper, sort of what does it mean that this algorithm is stronger and so on? It's not entirely clear. The other thing that I got to appreciate, but not immediately. So I've quoted several areas of application for the quantum technology: quantum chemistry, finance, investment, and AI. But if you dig deep into those problems, what exactly problems quantum computers are supposed to solve for these particular industries, it turns out it's all about optimization. Because in quantum chemistry, it is about finding for something called quantum Hamiltonian, the ground state of quantum Hamiltonian. That's an optimization problem of a peculiar type, a difficult one. It's not an easy problem, but it is an optimization problem. Finance, it's a portfolio optimization, either portfolio optimization or computing financial derivatives. These are optimization problems. So if there are limitations of optimization problems in general, I would not expect that the finance, by some miracle, would be better would be better off because of the quantum technology. AI. Why do we expect that quantum computers are particularly promising for AI? The quoted reason is stated as because we can use it to train neural networks. You might have heard the term training neural networks. You adjust the weights of the neurons so that they fit and the data the best and provide a good generalization and so on. Training neural network is is sort of a name of the game in every across the board in machine learning. What is the training? Training is optimization. You're trying to adjust the weights of the neural network so that you minimize the so-called loss function, and that's a minimization problem. Feeding to the data so that you have a good performance for your large language models and so on. That means minimizing loss function. That's a minimization problem. So all these quoted areas that have been quoted, in fact, are about optimization, not cryptography. That's a separate game, but others are. So let me talk about benchmark. To do a proper comparison of what the quantum computers can do for the optimization versus classical computers, we need to have a proper bench. We need to figure out how do we compare, that we compare apples and apples. When the quantum supremacy is being claimed, the nature of this claim is usually of the following kind. We ran our computer in much less time, and we have a better performance, better objective function, better value. Well, how do you measure time when it involves the quantum computer? That's not entirely clear to me. Because time is time, right? So even two different conventional computers, time, sometimes you have to use the CPU clock or something like this, but for quantum computer, what do you use? It's not entirely clear. There is a more honest way to do that, and I'll talk about that, but it's not done yet. And I doubt that the quantum computers of the day today will actually perform well in those in this proper benchmark. Benchmarking is an old story in my field of optimization. Pretty much this optimization was arrived. When optimization became such an important game, what happened was the sort of a community created a whole bunch of so-called challenge problems. These are particular examples, instances of optimization problems that anybody can try to solve, and it's a competition who does the better. So one example could be like a big giant network in which you need to find the largest number of known friends. It's called the independent set problem. That's a technical term. Another one could be like, who can solve the logistics problem the best? Another could be, who can pack the largest number of entries in a giant kind of a bag? Or who can solve the finance problems? And the list goes up. So there's a list of problems, and people compete. They come up with the algorithms, they can compete. One of the most celebrated, maybe, examples of this is something called the Netflix challenge. Have you heard about that? Netflix challenge. That's a challenge that was 10 years ago when Netflix gave its data and said, find me the best way of predicting the rating by the users in the movies. They depend a lot on the good quality predictions. Turns out that's an optimization problem of not too different from the dots packing in a network. So people compete, and the winners got $1 million from the Netflix, but it's just one of the many examples. You have a good algorithm, show that it works. So one of the organizations that runs this is called Dymax. They pose these problems, and people compete. And there's teams and teams and teams that they compete, and some are better, some are worse, and so on. So the compelling example would be if there is a problem for which somebody with quantum computer or combination of hybrid version, quantum and classical computer, can come up with a solution better than any other solution so far. Then it would be fairly objective thing. By the way, this is exactly what happened with neural networks. When Jan LeCun reinvented neural networks, what propelled him to celebrity was the fact that his new version of the neural networks did a better prediction on images by 10 and 50% than any other competition. And then, science or not science, he's doing better. This is something to pay attention. That would be very compelling. Only recently, because there was so much kind of a false alarms in the quantum supremacy in solving optimization problem, then people got together, and this is one of the recent publications in August. It's about suggested benchmarks for quantum algorithms to compete. So it gives a big list of problems and says, If the quantum computers are good, try it on these kind of problems. These are particularly good problems for the quantum computers to solve. It involves something called cubic or quadratic constrained binary optimization. Because of the physics connection, that's the particular nature of the problems in optimization that quantum should work well. Good. So, and practical advantage of the quantum computers solving those problems is questionable. I'm going to jump out of a little bit here. So I have a couple of slides here. Even though it's claimed, as I said, almost every I should mark the time, right? So how much time? When do you want me to shut up? Okay, 5 minutes. Okay, I'll keep it. I'll keep it in 5 minutes. Many papers that claim the supremacy as a present day reality. And this is I find it mind-boggling. But there's also theoretical barriers. Maybe in the interest of time, I will not go, even though I don't want to indulge too much into my own line of work. But basically, you can show mathematically there is a certain limits on what quantum algorithms can do. And yet there is so much belief, almost religious belief, that quantum can bring about advantage over classical computers for the optimization problems, that among very respectable colleagues, it's not like I'm not talking about crackpots. Really, I'm not going to say names, but with the very concrete, very respectable people who absolutely believe they can build a quantum algorithm that beats the classical computers better. It's almost as a religious belief, but what happens is that usually when they prove something, somebody else comes and say, you know what? In fact, we can have a classical conventional algorithm that does even better than your quantum algorithm. In that case, okay, but we will try this problem now. And then somebody says, no, you can actually, we have more classical algorithm. So that's kind of a game. We'll try this, try this. This reminds me, I cannot resist temptation. I'm in Italy, so this is this is a scene from my favorite movie, La Dolce Vita. I'm sure you know this movie, right? But Federico Fellini. So in this movie, as you maybe have watched it, there's an episode where two kids claim they've seen the Virgin Mary, apparition of Virgin Mary in the air, and say, we've seen it. And the whole town goes berserk. They run after that, the police is involved, people are fainting, there's a massive praise, and so on and so forth. And long story short, turns out the kids made it up. They're kids after all. But the public is not despondent. They say, okay, this was a hoax, this was not real, but I'm sure there's going to be another apparition of Virgin Mary. We will just keep searching. And this is sort of what reminds me of what's happening with the quantum dedication to find a quantum problem for which the quantum algorithm will build a classical algorithm for optimization. One of the reasons, very quickly, one of the reasons that particular type of quantum computers cannot build the classical computers is that, especially when they're in the so-called NIST regime, is because they're effectively localized and they cannot see the full network. And we have a paper about that let me pull the paper. It says QAOA quantum algorithm needs to see the whole graph. The point is that for certain type of problems like the packing the nodes without the friends, you cannot solve with optimality unless you see the full network. For example, you might not even distinguish that the fact that this network is for example, a dating network, and only connects boys to girls and girls to boys. When it's the case, you can pack half of the nodes. Half of the nodes, boys, are not connected to each other because they're connected to girls, or all the girls are not connected to each other. So optimal solution is half of the network. Without that structure, the optimal solution will be way, way less. Quantum computers cannot distinguish between the two because they're localized. The rest is mathematics. Let me wrap up and sort of share my thoughts on this. These are my only my thoughts. I am a believer in quantum computers and quantum technology. I think when they're built, it will be amazing. I just don't think that optimization and its sister versions is the right challenge for that. I don't think we will see the advantage in those problems. And for that, let me share with you another type of supremacy. I call it abacus supremacy. What's abacus? Abacus is this counting device. It was invented in Egypt. You probably know what it is. My grandmother was a bookkeeper. She had abacus. She could count, she could crunch the numbers very quickly. This is a very efficient, this is a very nice device. My grandmother was not a great mathematician or anything. She just learned how to do that. And if you give a challenge to two people, one with abacus, one without abacus wins. No doubt about that. You cannot do in your head calculations that you can do with abacus. Nobody needed to prove supremacy of abacus. Nobody needed to find some exotic problems for which abacus was better. It was just obvious. It's in your face. You see that it's stronger. And I think when the quantum computers are built, their advantage will be demonstrated in a very mundane task, like adding, subtracting, search, sending text, and not on those exotic and sort of peculiar and sophisticated problems like financial investment and derivative pricing or airline scheduling and things like that. That's prediction is a fool's errand, of course, but that's, I think, what that's the instantiation of the quantum supremacy that I anticipate will happen. Thank you for letting me share with you these provocative thoughts, and happy to take questions.
Yes. We have a microphone for questions. Okay.
I would be very interested to know, like, one of the examples of how benchmarking is used when trying to compare computers and quantum computers, because since they're two different kind of objects, it does not seem like trivial how you would compare which one is more efficient.
That's exactly the reason why. That's exactly the reason why doing this comparison is tricky. So when I said use those benchmark problems, it's basically a good challenge for any kind of problems. So there's a benchmark instances, and people compete and they come up with the best solution, and there's the best current solution. It gives you X. If you come tomorrow and reveal your algorithm, which happens to be quantum algorithm, or it's a combination quantum and classical, and it goes from X to X plus delta, good. That would be already compelling, because now we would know that somehow this advantage was obtained by the quantum device, right? And I wouldn't even need to worry about timing and cycles and things like that, because as you absolutely correctly said, it's not even clear how to compare or do those comparisons. So I'm just suggesting to compete in by absolute scale.
Okay, thank you very much.
Let's thank David again. Now, next speaker is Professor Vittorio Giovannetti, and he's full professor of condensed matter physics at Scuola Normale Superiore. So he got his PhD in the University of Perugia, and then he spent a period at MIT as a postdoc. And then he came back to Italy at Scuola Normale, and he also was my PhD supervisor. And he worked on several fields within quantum information. He gave fundamental contributions to both quantum communications and quantum metrology. So we talked about much ado about noise.
Okay, so thank you, Giacomo. I'm very happy to be here to give this informal presentation about quantum computing. So when Giacomo asked me to say something and to present something about quantum information and computing, it was not clearly clear to me what I should say and what type of subject I should take. But then finally I decided to discuss about noise, because I think that noise in quantum computing is one of the most challenging aspect of the problem, as some of the speakers before me already pointed out. So this is what I'm going to tell you. What noise is in quantum computing and how can we what can we do in order to avoid this type of effect. Okay, so I want to keep the discussion in a very informal level, so I will start with a quote of a very important character that is not a physicist, is not a scientist, is not even a philosopher. Is a writer, is an important British writer from the beginning of the last century. His name is Chesterton, and maybe some of you have read some of his beautiful novels. So he used to write novels, crime stories, where the main character was a priest, a country priest. His name was Father Brown. And in one of those stories, Father Brown solved a crime, and he made this important remark at the middle of the plot. It says, a wise man hides a leaf in the forest. Okay. And then the other guy that was talking to him asked, what if there is no forest? How can I hide my leaf? And then he said, okay, then you have to grow a forest to hide it in it. So now this quote doesn't really seem to fit in the discussion about noise, but as you will see, it is kind of connected. And I will come back to this quote later in my presentation. Okay, so now it's time to go to quantum. Okay. So as we have heard from my colleagues, quantum technology come with a very important promise. Some of them can be criticized, as David has done, but still many people in the field believes that quantum technology sooner or later will bring some very good news in terms of improving our computational tools or providing secure communication, as Marco have already told you. But even in other different sectors, like improving the precision of measurement, there are several fields that could benefit very much by quantum technology. Now, at the fundamental level, quantum technology starts from a very basic idea, which is, okay, typically we are thinking about storing and manipulating information by encoding such information in the digital form using special memory element, which we call a bit, that can take just two possible values. That's the idea of digital computation. Well, in the quantum world, in the quantum technology, you simply give up the idea of the bit and you replace it with another object that we call a qubit, which is a very small quantum system that can also take two possible states, but at the same time can exploit the fact that in quantum mechanics you have these things that is called superposition principle, and therefore you can have much more possible configurations. Yeah? Now, this is essentially the very basic idea that started this business and this type of search. And of course, is a little bit more than that, but that's fundamental. Again, quantum technology, by just using this idea of using as fundamental memory element quantum system instead of classical system, has a lot of powerful and possible important consequences. But together with the promise comes a problem. And the problem is that when you store information in a quantum device, this storing, these things that you are doing is problematic because quantum systems are very fragile. Okay, they suffer from the fact that typically they interact with other systems, possibly the environment, but even other qubits, other quantum elements. And this type of interaction, if not properly controlled, causes problem, destroy the information in a very, very fast way. And this is a big problem when you want to build the quantum computer. Now, so the presence of this effect turns out to be associated with what you may call noise. And we know very well what noise is. I mean, noise is not a specific feature of quantum mechanics. We know about noise, even the classical world. No? And indeed, it's just a byproduct of one of the most fundamental laws of life, which is the Murphy law, that says anything that can possibly go wrong, it will go wrong. So this is a very common fact that we know. No? Noise happens in everyday life and can interfere with the things that you want to do. The point is that, however, in quantum mechanics, noise is much more devastating than in the classical setting because, again, quantum systems are easily disturbed. And they can be disturbed by any type of interaction with all possible other degree of freedom that you have in your system. This is a very big problem, but it's not the only big problem that we have in quantum technology. The other very big problem that we have is that together with noise, we also have what we call quantum no-go theorems. What is a quantum no-go theorem? Well, a quantum no-go theorem is a statement about physics of the world, which comes from the very basic rules that quantum mechanics is based on. So there are things that you cannot do according to quantum mechanics. And among those things that you cannot do in the quantum world, there are things that you typically believe be possible because of your classical experience. So for instance, in the quantum world, you cannot copy a quantum state as you do when you have a classical message. If you have a classical message, we can copy as many times as we want. Like I'm talking to you about messages that I have written in my computer and I'm just giving it to you. And there is no problem with that. But in quantum mechanics, you can never do this. Yeah? There is an intrinsic impossibility, which is a law of nature. This is something that, as far as we know, is a true fact of physics. But there are other things that quantum mechanics prevents. So for instance, in quantum mechanical system, it is impossible to discriminate between any two arbitrary states. And also these things is very puzzling for us. If you ask me to discriminate between this mic and this other mic, we can easily do it. You know, this guy is sitting here, I see exactly where it is, and the other guy is like 1 meter apart. I can definitely distinguish the two. And there is no problem in classical physics for this type of things. But in quantum mechanics, no. There are some states that you cannot discriminate with certainty. And finally, there is another important no-go theorem. As a matter of fact, there are many, many no-go theorems. Here I just focus on 3 of them. One I didn't mention is the Heisenberg principle that was previously mentioned by Marco. But another one that I want to point out, which is associated with the Heisenberg principle, is the fact that in quantum mechanics, there are so-called information disturbance trade-off. What is an information disturbance trade-off? It's a fact which says that if I want to learn something about a quantum system, yeah, I can do to some extent, but there is a price I have to pay, and the price that I have to pay, that by measuring the object, I am forced to modify the object itself. And this is also a big problem when we are talking about information, because we want to read information. We want to make sure that the process of just reading is not interfering with the message I'm looking at. Okay, so together, the no-go theorems and noise create a big problem for us. But let's go back to the noise problem first, because it's the most intuitive one of the two. Okay, so now I want to discuss about noise, and I will discuss about it not in a quantum settings, but in a very simple classical setting. And to do so, I'm going to focus on a specific type of problem. Here there are two agents, two guys, Alice and Bob. Do we have a pointer here? Can I use it? Oh, yeah. So this is Alice and this is Bob, and they try to communicate. And the way they do, for instance, they talk to each other either on the phone or whatever. But unfortunately, due to the Murphy law, from time to time, the communication line gets disturbed by noise. There is some environmental effect that tends to deteriorate the signal. So Alice is saying something, Bob understands completely the opposite things. Now, this is a big problem in engineering, and people have tried to solve this problem and fix this problem for classical communication. And there are typically two approaches that you can achieve. Okay? There is a very brutal type of approach, which says, okay, let's simply improve the quality of our communication line. Let's try to make it better. Let's construct a new communication line which somehow protects our messages from the external noise. And this is a sort of hardware approach where you really go into the physics of the communication line and you try to fix it. It's very effective, but not always you can do that. There are some technical limitations, fundamental limitations that from time to time will prevent you from doing so. And therefore, people started thinking at other type of approaches, which are not hardware-like, but are software type of approach. And there are very simple ways in which you could try to overcome the presence of noise. So for instance, instead of saying the message one time, you repeat it. And you repeat it as many times as you want until this guy understands exactly what you said. So this is a very effective way of tackling the noise, even in the absence of an hardware protection to some extent. Okay, so this idea of using software to correct for noise goes under the name of error correction. Error correction is just a technique, essentially it's a mathematical trick, which rely on constructing the way you send the message using special codes. You don't simply say the things that you want to say, but you say them in a proper way that is less affected by the presence of noise. And the coding strategies that we adopt in classical settings rely essentially on two things. First of all, they use redundancy. Instead of sending a single message, I will send it many times. That is called redundancy. You repeat, which is essentially the things I'm doing now, because I'm repeating myself over and over about this concept. And then there is another part of the coding that is very relevant. So you send a message, the message gets disturbed. So for instance, the noise will flip one of those bits into the different value, a different value with respect to the one that you selected. And now what you want to do, you look at these signals here, one of those, it could be this one or this one or this one, it depends on the way the noise is acted. And you want to have a strategy to say, okay, I know that Alice was coding the message by sending 3 times of signals every time. So I know very well that most likely if I see 2 zeros and 1 single 1, this signal probably originated from the triple of 0. And therefore I should interpret this guy as a 0. So this needs a sort of decoding procedure that you can use in order to fix the effect of noise. And this procedure is based essentially on 2 things. The first thing that you have to do, you have to look at the message you received, you look at it, and depending on what you see, you decide how to modify, to interpret the signal. So it's measurement-based post-processing of the message. So as I told you, these 2 tricks together works very well. In classical information theory, they are heavily used and they help us to have reliable classical communication and classical computation, by the way. Okay, so, well, one way of approaching the problem is in the quantum setting is simply taking this idea and trying to translate them in the quantum world. Well, but here comes the problem. Because in the quantum world, first of all, the type of noise that our system is experiencing is very different from the type of noise that we have in the classical world. And as a matter of fact, there are zillions of possible things that can go wrong. While in the quantum digital setting, in the classical digital settings, the type of noise that you have are essentially of 2 types. First, you get a bit flip, or you can erase the bit. That's the worst that can happen. But in quantum mechanics, there are many different types of noise. And some of those noise are intrinsic into the construction of quantum mechanics. Like they are associated with the fact that if you measure, you destroy the system, you introduce noise. Or are associated with the fact that states which are not all the states are discrete, you can discriminate between them. This is an intrinsic type of noise that is part of quantum mechanics. You don't even need an environment to have that. The second thing that conflict with the coding strategy is redundancy. We have already seen that there are no-go theorem that prevents us from copying the system. We cannot copy the message. And finally, measurement-based post-processing, again, is problematic because if we measure, we disturb the system. So instead of correcting the noise, we are going to add extra noise in the code. And this is a very big challenge, or at least it was a very big challenge. It remains as such. Oh, sorry. I forgot one thing. So given this premise, you would be tempted to say, okay, there is no way we can introduce error correction code in the game. But that would be a very problematic thing for us, because in the absence of quantum error correction or error correction for quantum computing, essentially what will happen is that quantum computers will be at the same level of analog computers. Analog computers are classical devices that were invented in the middle of the last century, and they were very promising as a tool. They could perform very sophisticated tasks, but they have a very problematic issue. There is a very problematic issue is the fact that this guy, if an error happens inside an analog computer, you cannot fix it. This noise will propagate everywhere and the computation that you obtain is no more reliable. So therefore, you don't find in the market analog computer, you find digital computer, because for digital computer, there is error correction procedure. And therefore, this is the problem. If we don't have error correction for quantum computing, quantum computers will be essentially equivalent to analog computer. Nobody will try to build them. It will be a very nice idea to work with, but nothing more than that. Now, again, this was a problem till in 1994, this guy here, Peter Short, which is incidentally the same guy that he invented the factorization algorithm that before David was referring to, discovered that this problem that I have underlined before were indeed no real big problems. So you have to change the way you look at the problem, the way you look at the redundancy, measurement-based post-processing, and to reinterpret this idea in a different type of context. So for instance, one thing that you may notice is that it is true, there are a lot of different type of noise, but quantum mechanics is a linear theory. And this is, linearity is a concept that we have in mathematics. I don't want to enter into this. But essentially, when you have this type of linear properties in the model, these introduce a lot of symmetries or simplification. In other words, linearity can reduce complexity. And because you can reduce complexity, this very large amount of possible things that can happen, as a matter of fact, are not so many, because they are all connected through this linear type of constraint. On the other hand, instead of using redundancy, thinking about redundancy as something that forces you to copy the same message over and over and over, you want to think about redundancy in the quantum setting in the sense that what you want to really do is to take this information that you want to protect and distribute it over large many-body quantum system. You don't copy it, you simply distribute it somehow in a clever way. And finally, measurement-based post-processing. Well, if you look at what we are doing in the classical code, we are not really interested in the type of message that Alice was sending. What we detect is the presence of the noise. So we have to find a way in which the detection doesn't interfere with the message, but simply reveals what type of noise happened. If you use now this idea, you can indeed construct quantum error correction codes. So let me show you a very simple example of how you can build a quantum error correction code. This is a very trivial example. Indeed, this is the first type of code that was ever invented by Peter Shor. And it's the following. So you see here there is a quantum data, is the state of a qubit, which is a quantum superposition between two possible configurations, 0 and 1. And we cannot create a state in which this special state is copied 3 times on 3 different qubits. That's not allowed by the theory. But what you can do, you can write this same superposition in a different type of basis, in a state in which these 3 qubits now act as a unique body, as a unique object. And essentially, you distribute this alpha and beta that contains the information you are looking for among them. This information is no longer localized here or there or here, but it's something that is written in the full set of memories. So you see, here comes back our old friend Chesterton. So you don't copy the information. What you do, you hide information on a collection, on collective state, so that the noise cannot find it. So the noise is looking for this information, but it doesn't really know where it is. It can try to attract this qubit, but still there is something that remains in the code that we wrote that would allow us to understand what was the original message. Okay, so here comes what I call the Chesterton quantum forest. You have to build a forest where to hide your quantum leaf. And that is the idea of quantum error correction. So we are going to use very large blocks of quantum systems where we spread the information, and by spreading the information in such a way, we prevent the fact that when the noise acts on one of the physical qubits that we are using, it will destroy completely the information we store in it. So let me give you, and let me enter a little bit more in details into the functioning of this Chesterton quantum forest. So one thing that you want to notice, and this is a relevant thing to notice, is that when you study qubits, array of quantum memories, there is an important difference that you want to be aware of. The qubit can be arranged in space, like here. So these are real quantum memories that are sitting on in some place in very specific physical locations. This is the spatial configuration of your memory array. But the states where this guy lives, the state, the internal state of this object, does not really correspond to the spatial arrangement. Indeed, the theory tells us that the states that these guys can assume is associated with the configuration space, which is completely different from the spatial arrangement. So the spatial arrangement of qubit has nothing to do with the configuration space. If you want to, so configuration space is simply the catalog of all possible configurations that this qubit can assume. Okay? And this guy in quantum mechanics called the Hilbert space is a huge object. Okay? It's a big, very big object. Now, when we do coding, we do a very tricky things. So the idea is that when you encode information in the qubit, what you want to do, you want this information to be delocalized in space. You don't want this information to sit exactly in a given position. But at the level of configuration space, what you want to ensure is that this information is very well localized inside the Hilbert space itself. So you see, there is this double action that you do. I mean, these two plots represent the same quantum information, but in physical space and in configuration space. And they differ because here you delocalize and here you try to localize in a specific portion of the Hilbert space. Now, this is what you do. The noise, instead, act on the system in a very different way. Noise are things that happens in the real world. They act on physical qubit, on specific location. So the noise has a local operations here. And your code is built in such a way that at the level of the configuration space, this local action of the noise correspond simply into a modification of the location where you put the original information. It's simply like a translation inside the Hilbert space. Okay. And now you see exactly why you can correct. Because what I have to do is simply not to look here. You have to look there in the configuration space. If you look at the configuration space and you see that your quantum memory moved from that location to this location without looking exactly what is inside, that you don't want to do, you can simply undo the effect of the noise. And your information is back, safe, into the original spot. And you have prevented the action of the noise. So this is an amazing type of idea. It's a very powerful tool that Peter Shor was able to do. Now, what is the state of the art? We have nowadays very zillions of codes that play this game. at different levels. So we started from the short code, but then we have several of them. I don't want to enter into the discussion of all of them. The most successful one are more recent version of this idea, which are called surface code, which enables you to protect logical qubit in a way that they allows you to prevent a lot of noise, much more than the original shortcode could do. Sense. Okay, so of course there is a cost in all this business. And the first cost that you see is that in order to make safe some logical information, you need a lot of physical qubits. You need a huge forest of qubits to protect very a small amount of information. And this is a problem because it's cost a lot. The second extra problem is that when you code your messages using these special quantum error correction codes, then all the computation has to be done following the same type of reasoning. You have to work with this huge amount of qubit that store little amount of information, and you have to convert all your logical operation in this type of operation here. And this is also extremely costly, not easy to address. Now, this is pose also a problem which is associated with the fact that when you, so this, what I draw here is just a sort of quantum network, quantum circuit is a typical circuit that you see when you work in quantum computing. And now the idea is that each one of those lines codes a qubit in a protected way using this special coding. One of these lines is simply a big Chesterton quantum forest, and time goes from left to right. You want to take the information that is stored near and process this information, doing some manipulation here. Each one of these operations now act on a big forest setup. And the point is that you want to build your algorithm, you want to build your manipulation in a way that if one of those lines, one of these forests fails, or there is an error that happening there, this error do not propagate along the things. And so this is a challenge. This is a big challenge. But if you manage to construct configuration that prevents this type of spreading of the noise, you will arrive to what is called fault-tolerant quantum computation. Fault-tolerant quantum computation is an architecture that indeed uses this idea and enables you to perform computation without paying the cost of the noise that is induced by the environment. Now, in order to achieve fault-tolerant quantum computation, you have to make sure that at the hardware level, at the very physical level we started from, you reach some what is called a threshold value. So this threshold value refers on the type of level of noise that you have on each one element of the forest itself. Yeah? And people have tried to estimate what is the value that you have to achieve in order for this to be realized. Okay, so I think that I'm basically at the end of my presentation, and so this is more or less the state of the art of what we have. Again, we have the theory is well developed. We have new codes every day, but there is also experimental verification that some part of those codes can be realized in physical devices. So the most impressive one are these two. So for instance, this is the Google Willow chip, which allows you to encode information using 105 qubits, and it's worked very well. Another important result was obtained last year, indeed a few months ago, by the Harvard company Quantera, in which they developed a code using 400 and some qubits, and all of them have been implemented in real devices. Of course, this is just the initial part of this big construction. and so on and so forth. So I want to use this last slide to just say that we do have also a small company in Pisa, Scuola Normale, which is called Planckian, that is trying to tackle this same problem, starting from a different perspective, indeed, by using a new type of architecture, which is globally driven. I don't want to enter into this. And we are now producing our small devices. They are just little things, nothing to be compared with Google and others, but you know, we are there. So this is the end of my talk. I hope it was clear enough. Otherwise, I will repeat if you want. Thank you very much.
First of all, thank you for the talk. And my question is, redundancy is maybe the simplest thing that we can do to address quantum error correction. And it affects the hardware, basically. Like we put more physical qubits to embed into a logical qubits. But this does not feel very efficient, also because like creating GHZ states with many entangled qubits is very costly. So why would it be more convenient, if it is, to do this instead of like modeling the environmental noise with some master equations to address Markovian or even non-Markovian noise in that way?
Okay, yeah, of course, we can model the noise. One thing is modeling the noise. One thing is controlling the noise. Okay, so we have a very well understand. So we understand very much in a very precise way in which way the noise is acting on this device. That is not a big problem. With the theory of open quantum system is fully developed. We have a lot of mathematical tools to understand what's going on. The problem is, given that we know what's going on, how we do prevent that these things happen. And you may try to build better machines. You can try to screen the environment, but there is a limiting point that you cannot overcome. At the end of the day, whatever you build is an imperfect device, it's not ideal. And remember, in quantum mechanics, even the little perturbance can be devastating. So error correction is unavoidable at this level. This is a price that you have to pay. Okay. What you can do, you can try to reach this threshold I was talking about. You improve your hardware at the best you can. Once you are there, the theory tells you, look, you don't have to construct perfect devices. There is no need for that. Just construct devices which are almost perfect, with performance which are within the threshold I told you. And then you can just build the object using, scaling it as in a very simple way. So hardware solutions are good, but they are not the end of the story.
Thank you.
Yeah.
Let's thank Vittorio again. Let's move to the next speaker. Last speaker today, Professor Saverio Cataliotti. He's a professor of experimental physics at the University of Florence, and he got his PhD from the University of Florence, and he has been a prominent figure in atomic physics and all quantum technologies. In particular, he is known for his pioneering work on Bose-Einstein condensate and their applications, and the development of quantum devices for communications and sensing. Also, he's playing a role in national and international initiatives and quantum technologies. And he's talking about when qubits talk to each other. Please.
Thank you very much, and thanks again for the kind invitation. And as Giacomo was pointing out, I have somehow the opposite of what David was advocating. I mean, been working on quantum technologies, seriously working on quantum technologies more than 20 years ago. And in the last 5 years, I have been more involved into somehow the organization of them all. Okay, I will try to give some hints on, generally speaking, on quantum technologies and building on what have been said up to now. So thanks actually also to all my colleagues. Okay, let's see. Okay, yes. So what we are talking about is this so-called second quantum revolution. And here, besides the pleasure of showing Ted Ensho, who was one of my 2 PhD advisors, the other being Massimo Anguscio, the point that I would like to make here is that as we are moving in improving our technologies, the improvement of our technology, especially in terms of those who are used to manipulate information, brings the devices to smaller and smaller dimensions. That inevitably means that they have to that you have to take into consideration quantum physics. Whether this is a problem or an advantage is up to our fantasy, is up to our inventivity, to our creativity. So, given that there are different opportunities in quantum mechanics with respect to classical mechanics, this is where the whole thing starts. And as a message to older colleagues, this is also where we need to reskill engineers. Engineers forgot about quantum mechanics because the physicists made it too difficult. Now we need to have them back into the business. Now, the vision, the slides that you will notice different institutions appearing, because I've put together slides from different things, but I think it's also a good message to see who is coming into this. So for example, the vision, this comes from the European Defense Agency, is to have these technologies all across the different domains, from submarine to space, and handling information in different ways, acquiring, communicating, and elaborating the information. And this means that you have to create networks that are connected. Marco was pointing out in the beginning, securely connected, safely connected, but not only safely connected. If you want to take full advantage of quantum devices, you need to have them quantum connected. So they have to be entangled at a distance. So what are the different problems that you encounter? Well, just to finish the different institutions and mentioning what Marco was already pointing to, the European quantum communication infrastructure. This is a sort of dream infrastructure, unless but it's also a real infrastructure that we are building that has been started really to go towards what will be my last slide, towards a quantum internet. It's at the moment used to do secure quantum communication, quantum key distribution in particular, but is meant to be something that you update and upgrade as the devices arrive to go towards the quantum internet. I know this because at the time I was the Sherpa that wrote this declaration. So the idea was that we really had in mind something that we could improve as an infrastructure. The fibers were there. There are amplifiers. We need to substitute the amplifiers, first with trusted nodes, then with the quantum repeaters. The satellites are not there. We will put them up. They have to be quantum ready. We will have satellites to do laser communication in space because our bandwidth on Earth is finished. We have no more bandwidth for the Internet of Things that we want to build, not quantum, the classical one. We need new means of communication. This new infrastructure for communication has to be quantum ready. Otherwise, it will not be able to support quantum communication. And if we believe that the technology will go into quantum technologies, that infrastructure has to be quantum ready. So this is what it is behind this study of the EuroQCI. The Chinese have already a satellite in orbit. Europeans will put satellites in orbit, hopefully at the end of 2027. Now, means for transporting quantum information. Photons, they are nice. They move around, generally at the speed of light, which is fast, or as fast as you can go. They do not interact is something that has a question mark, but they can carry quantum information. And as for example, Marco was pointing out, you can actually use them to distribute quantum keys. And incidentally, that's the Turing Prize of this year. That's BB84, Bennett-Brassard 84 protocol, and Bennett-Brassard just received the Turing Prize. So this is a nice way of putting together the pictures that David showed in his first slide. And so you can use them to do quantum key distribution. So for example, this is a demonstration, a public demonstration that was done for quantum key distribution 3 or 4 years ago, actually 4 years ago, during the G20 in Trieste. We did a quantum key distribution network that was used to secure transmission between the location of the G20 in Trieste and 2 different locations in Ljubljana and Rijeka, so in 3 different countries, using a trusted node in Postumia. So it was a sort of a demonstration of a possible quantum key distribution network over the border. Was done with the help of an Italian startup, Quantum Telecommunication Italy, that we funded with a few colleagues. And this was done using fibers across the border. In Italy, we do have already a fiber backbone that was developed by INRIM together with CNR to initially distribute time signals, but can also be used to test quantum communication. And it can be connected to different things. So where does this stop? This stops because the photons are actually interacting with the environment. And we have 2 different problems that are coming in. One is that we lose the photons because of the Beer-Lambert law. That, of course, has to do with beer. The point is simply that as light propagates in any medium, light is absorbed. This means that if you're thinking of a continuous energy, this energy goes down. But if you're thinking of quanta, the quanta simply disappear. And so you lose your quanta, your photons during their transmission. And as has been pointed out many times, and as you can see from the words appearing there, this is not something that I did, but I took it from the internet. You cannot clone quantum information. We have seen that is impossible. Clearly showed that is impossible to reproduce an arbitrary quantum state. You cannot clone the system. So you have a problem because the photons disappear and you cannot clone them. So you need to solve this in order to extend, as Marco was showing, the communication. You can do that via clever ideas like that of the decoys, but you need something of a more general solution to go further. How do you get to this? Yeah, it will take a while. So let me start by changing the object that you use to transmit the quantum information, to store the quantum information, or to manipulate the quantum information. Photons have the problem. We get into another medium. For example, atoms. Atoms are nice. They have 2 levels, at least 2 levels. So they're directly usable as qubits. You can create superposition of those 2 levels. And with those superpositions, you can do many things. You can also do something that actually we had been doing for quite a while before recognizing that it's a quantum technologies. Although there is a little bit of discussion on this being a real quantum technology of the 2nd generation. The point is we have, for example, we have atom clocks. We have atom clocks that are actually realized by creating superposition of quantum states of an atom, a two-level atom in particular, for the current clocks of the two fundamental levels of the cesium atoms. You create this superposition, you let the superposition evolve for some time, and then you go and check if the evolution of your superposition is synchronized to some oscillator. And therefore, you resynchronize your oscillator to the atomic oscillation. And so the atomic oscillation is now your time reference. This is something that has existed since the 1950s. Is it a second generation quantum technologies? Yes, no, we don't care. The point is that it works with a superposition, and it works with two-level atoms. And it has been working for a long time. It's a great success. It's what you use for GPS, for example, but is now getting to some limit. This limit being the fact that we now would like to go beyond what is the precision attainable with those atomic clocks. And you see these atomic clocks now have this kind of stability. And this kind of stability can be surpassed if you go to optical clocks. So if you change the technology, not the principle. The principle is still a superposition of two states, but we are not using ground states. We are using ground state and a metastable state of not an alkali, but an alkali earth atom. And we hope, well, actually, we know that we will improve it. We already have it, but the definition of the second has not yet changed. For this, you need the link, an optical link, and this is why we had that kind of link I was mentioning, the backbone. But you can also use superposition to measure magnetic fields, for example. Or you can use superposition to measure inertial fields or gravity. You simply produce the superpositions of states that are not separated in energy, that are separated in energy, but this energy separation is affected by the presence of a gravitational field or by the presence of a magnetic field. And in this way, you can use the atom to sense these kind of fields. Okay, fine, great. We are banging into, again, a problem. The single atom and the single superposition can lose coherence. Of course, if you are interacting with an environment, the environment is also noisy, as Vittorio was pointing out. This noise, part of it you can actually use to measure what you want to measure, or actually is the effect you want to measure. Something else is going to destroy your superposition. And so you have a limit there. In order to go beyond this limit, you have to work with the collective state. But in order to work with the collective state, you have to do something different. So now you need to have the atoms interacting with each other. If the atoms do not interact with each other, you are restricted to working with the single atoms, many single atoms doing the same thing, but single atoms. So now, if you want to have something better, you need to have the atoms interact with each other. And the atoms indeed can interact with each other. For example, they collide. For example, they interact because they, when you excite them, they have a dipole, an electrical dipole. And the electrical dipoles, if you put them close by, interact with each other. So atoms can interact. And if they can interact, you can use this interaction to create this nonlinear interaction between the atoms to create quantum gates. Creating quantum gates means that you can create also more elaborate states. For example, you can use these atoms to create a simulator, a quantum simulator. A quantum simulator is basically a system. This was what was the Feynman original idea about using the quantum systems. You actually have you know that your fundamental in his case, a fundamental physical problem, is a Hamiltonian problem. That Hamiltonian is difficult to access and control, that specific Hamiltonian. You build a new quantum system that is regulated by the same identical Hamiltonian built from first principles in a way that you can actually, where you can actually engineer the interactions in the Hamiltonian, connect the single elements that are in that Hamiltonian, for example, if they are spins, the spin glass, the elements of that spin chain, and that will simulate your system. So this is an example made with atoms, arrays of atoms, and this is a way of actually creating a simulator. And you rely on the interaction between the atomic systems, between the atoms. But now you can also consider those atoms in pairs, and then if you are able to access the single atom in a controlled way, you can actually build a quantum computer in the same principle. This is the Cuera principle that Vittorio was mentioning. They have single atoms localized in optical tweezers. They can access those atoms. They promote them to a Rydberg state where the atom has an electrical dipole. This will interact with another atom that has been promoted, creates the interaction. Then you go back down with a dephasing. That means that the two atomic states have been entangled together. So now you have a delocalized quantum state over the network. This is something that has been done by many groups, and in Firenze we have the last edition, at least for the moment, of this system. It's a small one, but at least we can play with it, realized within the framework of the National High Performance Computing Center. Okay, what about the sensing problem that I was mentioning before? Now that we are able to create superpositions of many atoms, you can actually access something that is called the Heisenberg limit. When you are trying to measure with individual objects, you repeat your measurement basically n times, one every single object that you have. And the scaling of your precision goes as 1 over n, the number of objects. If you are able to create quantum superposition of different objects, more precisely, quantum entanglement of different quantum objects, the scaling improves to n squared. And when n is 1,000, n and n squared are two very different numbers. And this is why you try to have these interacting systems to do quantum measurements, to do actually quantum sensors. This is an example with Bose-Einstein condensates, the scaling, the Heisenberg limit with respect to the standard quantum limit. You can actually take advantage of different kind of interactions. Possibly here, I don't want to get into much detail, but the idea is you repeat the same kind of interferometric scheme that I was showing you with free-falling interferometers with trapped atoms. And in this case, the atoms have time to interact. If they have time to interact, they have time to form these collective quantum states. And if they form the collective quantum state, you have an improvement on the precision of your measurement. Okay. But atoms are also nice because they have more than 2 levels. Indeed, atoms have always more than 2 levels. There is no such thing as a 2-level atom. The 2-level atom is just an approximation where the other energy levels are far away, okay, with respect to this distance in energy of the two you are considering. So if there are other possible atoms, you have a more complicated thing. And as an Italian atomic physicist, I'm very, I have a lot of affection for this system because this is one of the great successes of the Italian atomic physics, the observation of the so-called riga nera. It's a dark resonance, is the first example of quantum interference in an atomic system. This comes about because of the presence of 3 atomic levels, and so 2 possible paths to connect the ground states to the excited state. And every time you have 2 possible paths in quantum mechanics, you have an interference. And the interference in this case is destructive in absorption. What happens is that the light of one of, if you want, is destructive in the population of this level. Normally, if these are 2 ground states and this is an excited state, normally the population resides down here. And the funny thing is that if you connect both levels to the top one, instead of increasing the amount of atoms you store up here, you decrease them. And you see this as a reduction of the fluorescence in the exact at the exact frequency. Here the frequency is actually distributed in space. Let's not get too much in detail, but it's distributed in space. So you see at a very specific point the destruction of this population. This can be interpreted in other words, because this is an experiment of the 70s. It was reinterpreted in the 90s by Steve Harris as electromagnetically induced transparency. The main point, the big contribution of Harris is noticing that there is, of course, this distraction of absorption that was already noticed by Gozzini and his group, but there is also a very steep dispersion. Now, dispersion in the propagation of light is connected to the speed with which light propagates. Okay? If you have a very steep dispersion, this means that your speed is very, very much reduced. And the important point is that is very much reduced the speed of propagation in the same range where the system is transparent. So the light propagates without being absorbed, but very, very slowly. Very slowly means that you can actually stop it and freeze it. So you have to do some procedure. I don't want to get too much in detail, but it has to do with using a control field that you can actually change, whose intensity you can actually change in time, but you can store the photon into the atomic state. This means that you can actually stop the photon in the atomic state, or in terms of quantum information, you transfer the information from the photon into the atomic state. And hopefully it stays there. Of course, there will be decoherence, etc., but this is a way to create a quantum memory. These are the steps, basically. You have a control field, you have your photon entering the system. It's really impressive when you think of it. You have this object that we think of as a photon that, since it's very, very, you know its frequency very, very well, it means that you have no idea where it is. These guys are something like kilometers of length or hundreds of meters of length, photons. They enter a 10-centimeter cell and they squash into things that are few millimeters. And you can actually then, because the reduction is the ratio of the speed of light to the speed with which they move in the system, it is centimeters per second. And then you can actually switch it off, switch the control field off, and trap the light inside your system. And then you can release it by switching on again the control field, and the light exits the system. So it's quite impressive what happens in these systems. Of course, this is a way to create a controllable delay and resynchronize all your quantum systems at minimum. And this is an essential ingredient to solving the problem of doing a quantum repeater. Now, I think we have 10 minutes or no, less. 5. Okay, I'll accelerate. Okay, these I can skip. You create single photons in some way, and you move them around. Now, this is a way to create not only single photon, but also entanglements of photons. And when you create this entanglement of photons, you can actually create pairs of entangled photons. And if you want to extend the range of those pairs, you have to introduce this so-called quantum repeater. What is a quantum repeater? Basically, you have two sources of entangled photons that are separated by some space. These two photons are propagating in some directions. You take one element from each of the two couples and you perform the so-called Bell state measurements. So I don't know if you're familiar with this. Hopefully you are. Otherwise, you have, I try to quickly tell you, if you have two-level systems, there are states, the so-called entangled states, that are not separable between the two single quanta. And these are called entangled states. A basis for all these states is the so-called Bell basis. The Bell state bases are 4 possible states that are 2 photon states, not single photon states. So if you're able to do a measurement discriminating these 4 2-photon states, you are able to swap entanglement between these couples, the couple here and the couple here. You do a Bell state measurement on the middle systems and you swap the entanglement to the outer system. This allows you to extend the entanglement range to the 2 outer systems, and if you repeat it with high enough efficiency, you create a repeater, a quantum repeater. What is the problem? The problem is that the Bell state measurement requires some sort of form of nonlinearity. Otherwise, you are stuck with 75% efficiency, which not necessarily is enough. And this requires the presence of a C0 gate, at least. There are other ways, but at least some form of nonlinearity. So that's where we are, more or less. People are trying to create C0 gates. This is I just put this up not only because it's one of my old proposals, but because it's on a funny review. It's Optica, it's a Russian journal. When in the early 2000s, we did publish on Russian journals. Now we cannot do it any longer. But it's a funny proposal to create a possible quantum gate with photons and the nonlinear interactions. But so the idea now is we are trying to get more efficient Bell measurements and more efficient quantum memories, combining those things together to create these quantum repeaters. Once you have them, you will be able, and this is basically my last slide, you will be able to start thinking of creating a quantum internet. Quantum internet is not the same thing as the current internet. It's something different. Quantum internet means that your superposition, or actually your entanglement, is distributed over a continent in the large scale, at least over tens or hundreds of kilometers. This might be of use for connecting quantum computers, and it could increase, for example, the possibility of doing powerful calculation. But as a physicist, it's a fantastic physics problem. We have absolutely no idea of what is going to happen when you have a superposition that is so extended. What is the decoherence that comes in? If in any way it shouldn't, if in any way depends on the distance, it should not. if in any way it scales with the difference in energy. It should not. But once you have larger and larger objects in physics, as any time you have been able to produce bigger objects or being able to look closer to something, we have discovered something. So creating this superposition has a lot of possible applications, but is also a fantastic physics problem. And with this, thank you for your attention.
Undersea undersea quantum communication
Yes.
type of project. Can you say something if you can?
Yes, I can. There are different things. The part that I can certainly say has to do with the fact that you can use underwater fibers to do quantum communication. And this we have already done between Italy and Malta. And we have a project within the EuroQCI. The EuroQCI is also a program that has different steps. First step was produce European devices. So the Commission financed a certain number of companies to start producing quantum key distribution devices. One is in Italy, is Telsi. And then there is Team Quantum as well, but this was financed with the second group, the second batch. Then they developed that we all developed networks within the countries, and now we are developing the cross borders. The cross border that Italy is testing is one between Italy and Austria, and this is ground, and one between Italy and Greece, and this is underwater.
Yeah.
So this is an underwater communication. Then we are also trying to do a free space underwater communication, but there I can say.
So, but what is the intrinsic advantage to go underwater?
With the fiber is that is enormously less noisy. And also sometimes you have to do it because there is no other way of doing it. Most of the fibers are underwater and not underground. The main problem is that fibers, as far as I know, underwater are placed already with amplifiers. Whereas if you want to have efficient quantum communication, you have to get around those amplifiers. And placing a fiber underwater is expensive. So we first have to understand exactly what works and what doesn't work.
Okay, thank you.
Other questions?
Thank you. You mentioned about satellites. You mentioned satellites for communication. Can you use the same system, satellites mixing with fiber optics, or they talk differently?
No, it's exactly like that. The EuroQCI has a ground layer that is fiber optics, and the satellite layer that is optical satellites. You cannot use the conventional microwave satellites. Now communication is done with microwaves. To do quantum communication, you have to do optical, so we have to use optical satellites. The first European satellite will be placed in orbit. It should have gone in orbit this year. It will go hopefully in orbit next year. It's gonna be a low Earth orbit. It means that it's close to the lowest possible orbit, close to ground. This also means that these satellites are going to move very fast overhead, but so you need tracking systems. What we are now developing is optical ground stations. The Italian Space Agency is developing 2 optical ground stations. One is in Matera, and one is a mobile system.
Thanks.
Not stand. let's thank all the speakers, all of you who participated in this event. And I did it.